Hello everyone. I am Ravi Ranjan Singh. I'm currently pursuing my MTech in cybersecurity at IIT Delhi. Today, I will delve into my research project on adversarial machine learning attack targeting the network intrusion detection system. With the proliferation of the network devices, safeguarding network from various security threat has become a paramount. Network attacks can compromise data systems and network integrity. One crucial defense mechanism that is used against such threat is a network intrusion detection system. Now let's see what is network intrusion detection system. Network intrusion detection system monitors the entire network and identifies the potential threat to the network devices. As shown in the diagram, the network intrusion detection system is mostly placed in between the internet and the trusted network. It detects if whatever the traffic comes, it detects if it is a benign traffic or a malicious one. If it is a malicious one, it discards the packet, and if it is a benign, it forwards the packet towards the trusted network. A typical NIDS basically consists of three phases, that is monitoring, detection, and response. The monitoring phase measures the network state by collecting the statistical features such as number of packets sent by a device or the connection made. These features are used in the classification phase where a ML algorithm determines whether the monitored feature exhibits the property of a potential network attack. According to the classification phase result, the system responds with appropriate action to defend against the attack in a response phase. Now, based on the attack detection paradigm, NIDS is broadly classified into two, that is, signature-based NIDS and anomaly-based NIDS. We will look at one of them. We will look at both of them one by one. Now, the signature-based NIDS basically extract the signature from a payload of the packet and matches with already existing signature in the database. Now, the problem with the signature-based NIDS is that it is not secure against the zero-day attack. The zero-day attacks are basically the attacks that have recently that have been launched for the first time. And secondly, they are prone to the signature obfuscation. The other kind of network intrusion detection system is an anomaly-based NIDS, which basically trains the ML model on the benign datasets to detect the occurrence of the network attack. Now, the anomaly NIDS are basically uh, they could they basically could prevent the zero-day attack, and also they are prone. Also, they are safe against the signature obfuscation. Anomaly-based NDS are prone to mimicry attacks, where an attacker modifies the attack features to make them similar to the benign features. Now, let's try to understand what exactly is the problem statement that we are trying to solve here. Now, most of the NIDs uses the DNN due to high detection accuracy, but this makes them vulnerable to the adversarial attack. Now, let's see what exactly is adversarial attack. Adversarial attack perturb the malicious data in a such a way that it is being identified as a benign by the model. Here you could see the packet from the internet is sent to the NIDS, and based on the trained ML classifier model, it classifies them as a benign or malicious. But the attacker could fool this model by making the perturbations in the malicious packet that causes the model to detect it as a benign. Such attacks are known as adversarial attacks. Now, there has many such feature level attacks that have been proposed in the field of computer vision, but these attacks cannot be directly incorporated in the network to test the robustness of an IDS, as network data are sequential data, unlike the image data features, which are not much interrelated. For that purpose, we need to come up with a such adversarial attack that could check the robustness of the current NIDs in the market. So let us first understand what are the existing works that are done in this field. Majority of the studies in adversarial learning against NIDs directly implement the adversarial attack designed for the computer vision, ignoring the fundamental difference in the detection pipeline and the feature space between the computer vision and NIDs. Most of the attacks that are done in NIDS are the feature level attack taken from computer vision. In case of feature level attack, the small perturbations are made to the feature of the data set to bring the classification results in favor of the adversary. These attacks are not effective in case of NIDS, since the NIDS the features are sequentially and inherently related, and changing the features won't always lead to a meaningful packet. So there is a need for the packet level attack on the DNN based NIDS, and we have implemented one such attack called LM attack on the Kitsune NIDS. which is the ANN-based NIDS, in order to check the robustness of the Kitsune NIDS against the packet level attack. To understand the attack, we need to understand the working of Kitsune. Now, Kitsune is a network intrusion detection system based on a neural network and designed for the effective detection of abnormal pattern in the network traffic. It operates by monitoring the statistical pattern of recent network traffic and detects the anomaly pattern through an ensemble of autoencoders. Now, each autoencoder in the ensemble is responsible for detecting the anomalies related to a specific aspect of the network behavior. Ensemble layer consists of large number of autoencoders. After the feature mapping, the cluster of features are mapped to these autoencoders, which after encoding and decoding of the input feature calculate the RMSE, which is passed to the output layer, that is anomaly detector layer. Now both feature mapper and anomaly detector layer works in two mode, that is the train mode and the execution mode. Now, in order to better understand how Kitsune work, we will describe the process which occurs when a packet is acquired. First, the raw packet is being taken. The raw packet is passed to the parser, which basically passes the packet. And after the packet has been passed, we need to do the feature extraction on the packet. The feature the the feature extraction receives the FE receives this information and uses it to retrieve over 100 stats, which are used to implicitly describe the current state of the channel from which the packet came. Now, these stats forms the instance X, which is passed to the feature mapper. The feature mapper operates in basically two modes. One is the train and the other is the execution mode. During the train mode, feature mapper uses the data and receives uses the data that it receives to create a map that groups similar features together, but it does not send anything to the anomaly detector until this map is complete. Once it's done, the map is sent to the anomaly detector, and the anomaly detector uses it to set up a system of autoencoders, each handling a specific group of features. In this mode, in the execution mode, the mapper uses the learned map to split the data into smaller pieces called instances. These instances are then sent to appropriate autoencoders in anomaly detectors and symbol layer. The anomaly detector receives the instances. During the training mode, AD uses the instances to improve its ensemble layer. It calculates something. It calculates something called RMSC. The largest RMSC from the output layer becomes the threshold. Becomes the threshold. Then during the execution mode, when the AD process these instances, so all its layer, if the RMSC from the output layer is higher than the threshold value, it raises an alert and log details about the packet. And finally, the original packet and instances are no longer needed and can be discarded. This is the whole pipeline. This was the whole pipeline of the Kitsune architecture. Now, in order to perform the attack on the Kitsune NIDS, we need to make sure that the Kitsune is working properly. For this, we perform the following tasks to set up a Kitsune NIDS. We implemented the Kitsune pipeline model. This would make tracking of different steps of Kitsune easier. We trained the model on the benign dataset, that is Google Home Mini dataset. The testing is done on the attack datasets, that is port scan datasets, and the results were produced corresponding to that. We built the Python library that encapsulated the Kitsune implementation so that it could be called directly when needed. Now, this is the graph plotted for the Google Home Mini. The graph is plotted between the timestamp and the RMSE log scale value. The color is allotted to the points based on the log probability of that RMSE. The more is the negative value, lesser is the probability of occurring that value. Since for the case of attack, the value that are obtained are least probable, so their log probability value would be highly negative. In the above graph, as expected, almost all the data is identified as benign. The graph on the right is output of passing the port scan dataset from the Kitsune NIDS. As expected, most of the data in yellow and negative region, which shows that the Kitsune is correctly identifying it as an attack dataset. This shows the proper functioning of a Kitsune network intrusion detection system. Now, after setting up the Kitsune NIDS, we went ahead to implement the LM attack on Kitsune. Now, LM attack is a transferable gray box attack, and here we have the access of the training data of the Kitsune NIDS. Now, what we did is we created a surrogate DNN model and trained the model on the same benign dataset on which we trained the Kitsune NIDS. Later, we pass the malicious packet through the surrogate model, and if it is being identified as benign by the surrogate model, we add that into the output packet. If it is identified as malicious, we perform the packet mutation on the malicious packet. The best mutation is chosen using the PSO-DA algorithm. After the mutation, the packet is added to the output packet, and we further pass this packet to the Kitsune pipeline. Uh, we could better understand it through this diagram. Here you can see that the input packet containing the malicious packet is passed through the surrogate model. The surrogate model classifies each packet as either a benign or malicious. For each malicious packet, LM finds an optimal mutation operation that minimizes the anomaly score produced by the surrogate model. Next, the mutation operation is applied to the malicious packet to generate a set of adversarial packets, including the original packet and redundant packet. Finally, the benign and adversarial packets are written in place of the output file. Now, in the objective function that we are using here, the M is the space of all possible mutation operation, and small m is the specific mutation operation. Pi is the ith malicious packet, and ith malicious packet. P dash is the set of adversarial packet after mutation. The aim of the objective function is to directly minimize the maximum anomaly score of the adversarial packet that are obtainable with the mutation operation on the malicious packet. Since LM operates under the gray box scenario, we calculate the anomalous score based on the G dash, based on the surrogate NIDS that uses an arbitrary outlier detection algorithm. Although the surrogate NIDS will have slightly different decision function and anomaly threshold, we still expect that the adversarial example that bypasses the surrogate NIDS to also bypass the target NIDS due to the adversarial transferability. Now, the graph represents it over here. It represents how the benign data set is being interpreted by the Kitsune NIDS. The red line in the graph represents the threshold RMSE value. So, the most of the value in the above graph is below the threshold. The false positive curve shows that as the threshold value decreases below the certain limit, the false positive rate increases drastically. Now, this is the result for the case of the surrogate NIDS. Surrogate model is a machine learning model that is trained to mimic the behavior of the Kitsune model. The graph here represents how the surrogate NIDS is behaving in case of benign dataset. As you can see, the most of the traffic RMSE value is below the threshold value, which represents the surrogate model is correctly identifying the benign dataset. The false positive curve shows that as the threshold value decreases below the certain limit, the false positive rate increases drastically. Now, uh, here in this graph, we could see that for the attack dataset, the RMSE values are above the threshold value, and the threshold value at which the false positive values start increasing is quite high, which shows the characteristics of a attack dataset. Now, these two graphs basically represent the results for the case of adversarial packet. As you can see, for the case of adversarial packet, the graphs are quite similar to that of a benign packet, since most of the missing value of most of the packet is below the threshold, and for the case of false positive rate, um, the false positive rate also start increasing after a lower value of the threshold as compared to the attack data set. Now, now let's come to the effectiveness of an attack. Now, the following points basically shows us that the attack that we have performed is effective because the first is the threshold for the Kitsune. This is the threshold for the Kitsune NIDs, and this is the threshold for the surrogate NIDs. This, as you can see, that both the thresholds are quite close to each other. This shows that the behavior of the surrogate model is very similar to that of a Kitsune NIDS model. Now, evaluation metric for Kitsune represent that most of the adversarial packet is identified as a benign traffic. Hence, the true positive value is quite high. And as a result, precision, recall, and F1 score of attack is high. This shows that the attack is effectively working in our case. Now, by taking the idea from the LM attack model, we basically created a model that takes the malicious packet and adversarial packets rated by performing the mutation on the malicious packet. We are generating new packet and checking its similarity to the adversarial features. To do so, we are using a searching algorithm called like PSO. It gives the optimal mutation value to maximize the similarity. Now, the similarity value is calculated based on the fitness function, which is basically the difference between the adversarial features and the new feature. By difference, what we mean is the L2 difference between these two features. Now, the packet generated corresponds to that comes as the packet generated corresponding to that comes as a replay packet, which could be later used to perform the attack. Now, from these results, we can infer that for the case of replay packet as well, the NIDS is identifying most of the packet as benign, which shows that the Kitsune NIDS is successfully fooled by the LM attack. Now, this inference is basically based on the fact that since we can see that most of the packet RMSC value is below the threshold value, and the FPR value at which means the threshold value after which the FPRs begin to increase drastically is also quite low. No, the aforementioned results demonstrate that even if a secure network intrusion detection system such as Kitsune can be vulnerable to a packet level attacks like LM, the attack method used in the LM attack can effectively convert many feature level attacks into a packet level attacks, making them more effective against the NIDs. As a result, in future research, we aim to develop a new attack technique that utilizes the replay packet generation feature of LM attack combined with the concept of generated feature level attack on computer vision or NIDS. We can leverage the finding of this study to evaluate and generate a replay packet for the new attack techniques that we will test in the future. This study can establish a solid baseline for the future attack that we will conduct on NIDS. Thank you.